All right, here we go. Lesson 3.2 on Gaussian elimination. Now, I'm probably going to be talking for a fat minute here because there is a ton of new vocabulary here. Now, a lot of it, in the grand scheme of things, in your high school career, this vocabulary is very advanced. You might be, honestly, you might be a college student right now stumbling upon this video trying to learn about Gaussian elimination because this is a college level topic. And I am going to go pretty in depth, not super in depth, not crazy in depth, but enough to know vocabulary of what we're doing here. And that's what the first few minutes of this video is going to be. So before we even talk about Gaussian elimination, this is a whole new thing for you guys. We're going to talk about a matrix. So let me get my laser pointer here. Matrix. And yeah, okay, I've got most of it written out here, but I do want to explain in this video kind of like I would in class, okay? A matrix, plural matrices, is a way of arranging data, all right? Now, in particular, it's a rectangular array of quantities or expressions in rows and columns. Every matrix is constructed of some amount of rows and columns, okay? Now, we're talking about system of equations. So I can arrange the coefficients of a if I have a system of linear equations, I can arrange the coefficients of those equations into a matrix called the coefficient matrix. This coefficient matrix is just an array of the coefficients of each variable in the system. So here's an example. I know I'm using a ton of new vocabulary here, but to show you what this looks like, what does a matrix look like? Well, I said it was in a rectangular array, right? So this fella, I'm going to use big old brackets like this. Actually, I wonder, will the application... Look at that. look how cool this iPad is, right? I can make nice straight bars if I really want to. Nice. Okay, that's not perfect, but whatever. I don't care. I was just testing that out. Sorry, I was just having fun there. Okay, so a matrix, I'm going to use these square brackets, and I'm going to arrange the coefficients as such, left to right, down and up. So if you remember from the last lesson, I told you it was important to align your variables. This is why. My x's are in columns, my y's are in columns, right? But the equations are in rows. So I'm going to write the coefficients in a sort of array here in columns and rows. 2, 3, -1, and 4. Notice, right? This is 2 times x, 3 times y, -1 times x, 4 times y. And this will be written... Sorry, this is bothering me. If the left one's going to be imperfect, then the right one's going to be imperfect. There we go. That looks better. Now, this particularly can be written like this, where it's the coefficients times, what would you call this, the vector of variables? I don't know. Lacking the vocabulary there. But this guy means the exact same thing as this. But I'm not going to bother writing the XY here just because I don't want to get too in-depth in matrices right now, okay? There's a lot that goes with this stuff, and this is just our introduction. Next, we're going to introduce the vocabulary, an augmented matrix. So an augmented matrix is used to append. Append means add, right? So I'm going to add something to my matrix. A column of the constant terms from a system to the coefficient matrix. And I say it essentially organizes all the information from the system of equations. So observe, I have a system of equations here. I am going to rewrite this as an augmented matrix, meaning the first part is the coefficient matrix, and the second part is I'm adding a column at the very end that is my constant terms. So I will draw my square brackets. You must have these square brackets to say that this is a matrix. I will say some people sometimes use parentheses, and sometimes people use straight bars. For us, just do what I do. Just use square brackets, okay? But if you want to use straight bars or big old parentheses, you can, because that is still a matrix. It's just a way of indicating an array. So I'm going to first, let me write my coefficients here. 1 on x, 1 on y, -3 on z, and then on that last part is -6, right? So over here I'd have -6. On the next row, I have 2x, so there's 2. Notice now it's -4z. So if you're keeping track here, the first column is x values, the second column is y values, the third is z values, and then the last one is your constant terms. So I'll use my laser pointer here, this equation has no y value, which means you have to assign a value in the matrix for this as a coefficient. If I don't have a y value, the coefficient on that y is 0, because there is no y. 0 times y, there's nothing there. And then -4z, and then -10 is my constant. And then on the next row, notice there's no x here. So I have 0 x's, I have 6y, 9z, and then 39. Okay? But I did mention this idea of appending. So I'm going to separate my coefficient matrix from, what do they call this? The vector something matrix? I can't remember. Sorry, I don't have all the vocabulary in my head. A lot of this is really advanced college stuff. I'm going to put a vertical bar like that. Do you see what I did? I'm going to erase it and put it again. A vertical bar separating my coefficient matrix from that thing I appended to it. Okay? You see that, right? See how this is the coefficients? So these are these coefficients, but then the constants I arrange on the other side. Okay? Okay. So you have to know how to arrange that. And that's the easy part. All right? That's the easy part. So Gaussian elimination is an elimination procedure that aims to eliminate variables in a system of equations one by one until there is only one variable left. Of course, we're going to explain what that means in just a second. In Gaussian elimination, we're going to use what's called elementary row operations on this augmented matrix. So I might have something like this to start with. I'm going to use what's called elementary row operations on the augmented matrix to get it in a certain form, okay? And we're going to talk about that. There are 3 rules, however, for my row operations. Rule 1, you can interchange any rows. So if I wanted to swap this top row with this bottom row, I could do that. It's fine. It doesn't really matter the way I arrange these systems of equations, as long as, each equation is still with itself. The next, number 2, I can multiply rows by non-zero constants. Constants, so when you deal with matrices, you're going to deal with stuff called constants versus vectors, I think. So there's a difference between the two things. So a constant is just some whole, well, not even whole number, but just a number that you are multiplying by. I notice, say, non-zero, don't ever multiply by 0 that accomplishes 0 things, okay? So don't multiply by 0. And the last one is I can add a multiple of one row to another row. So essentially, step 3 is I can multiply a row, and then I can tack that on to another row. And you don't have to multiply. I mean, you could keep it as is, right? Like just add a row onto another, and that would be fine, okay? All of these, you are really, when you've practiced elimination in the previous lesson, all 3 of these things are what you're doing. But now it just looks a little bit different. Okay, let's move on. Okay, so the goal of Gaussian elimination is to provoke, like I said, row operations on the augmented matrix until either one of the two is achieved. Number 1, the augmented matrix is put into row echelon form. From here, you can use simple substitution to solve for the remaining variables. So what is row echelon form? Well, row echelon form is when you have, it's like, I have like, let's see, 1, and I say 3, 6. No. Is it ones? Yeah, it is. So let's say I had a 3 by 3 matrix. I have a diagonal of 1s with 0s beneath them. And then I could have different numbers all aside. And then my augmented matrix, I might have, some constants over here. All right? So that right there, what I've done is row echelon form. This is a visual example. Number 2 is an augmented matrix can be put into row reduced echelon form. Each variable is now known since the coefficient matrix is now the identity matrix. And so I'm throwing a ton of vocabulary here at you. Row reduced echelon form looks super similar, but it's a diagonal of 1s with 0s in every other place. I might say like -3, 6, and 2. So notice the difference, right? Row echelon form only has, both of them have this diagonal of 1s. That's key. You have to have this diagonal of 1s. But the row echelon form has just 0s beneath, and the row reduced echelon form has 0s on top and bottom. Okay? I like this one. And if you're taking a linear algebra course, you're probably having to do it in row reduced echelon form. We're fine to stop here in row echelon, but I am going to show you both. I will. I'll do both. So you can kind of see both in action. If you do get it in row echelon form, just in case you're watching this, this is known as Gauss-Jordan elimination. I'm not going to keep that in my notes, but I wanted to write it out. If you stop here at row echelon form and use that to solve the matrix, that is known as the Gauss-Jordan method. Whereas finding the identity matrix is row reduced echelon form. That's true Gaussian elimination. In fact, I might even add that thing is the identity matrix. That's what that is. That little row of ones, yeah. So again, notice what I say here. What you are trying to do is use elementary row operations to make the diagonal of the matrix all 1s, and to create what's called an upper triangular matrix. So the diagonal of a matrix is quite literally the diagonal, all right? It's for square matrices, so 2 by 2, 3 by 3, 4 by 4. The diagonal is just diagonally crossed from top left to bottom right. The upper triangle matrix is this. Okay, it's really just row echelon form is your upper triangular matrix. But if I were to give an example for upper triangular, it's not here, let me switch back to red. Sorry. An upper triangular matrix looks like this. I don't have to have that diagonal of ones. I could have like 3, -2, 8. But I do have the zeros down there, and then I could have anything up here. Like so. Okay? So what I'm going to do I have a highlighter? Yeah. Highlighter. That's my triangle. Can you see it? Can you see that's a triangle? Boop. 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 That's my triangle. For upper triangular matrix, it just means have zeros below the diagonal. But row echelon form is have those zeros, have that upper triangle form, but also have a diagonal of ones. Okay? And to get these, we're going to use row operations to find this result. I also have a little note down here. If you want to know what this word echelon means, in military lingo, this is like a type of formation. So if you've ever seen birds flying, I'm going to do a little example here. How do I draw birds? Okay, bird 1, bird 2, bird 3, bird 4, bird 5, right? Birds fly in that kind of formation. Same goes for aircraft. You'll see planes, right? Fighter jets do that. Sometimes troops do, right? Ships, vehicles, all that kind of stuff. So that's why we call it echelon, because it's like the birds are arranged diagonally. It's diagonally a thing of ones. So that's why we use this word echelon. Okay. All right. Here we go. Example 1. Now, I'm going to say it is extremely important to show your work on this. And honestly, not even because I'm grading it. It's just important for you to show your work so that you can follow your own work. If you try to do this mentally, you will likely make mistakes. It's very tough to do this mentally. But here we go. Let's try it out, okay? I'm going to model how to do this. So first things first, example 1, solve this 2x2 system of equations using Gaussian elimination. So first thing, I'm going to convert this into an augmented matrix, the coefficient matrix, and then my constants tacked on. So the coefficient on x is 1, the coefficient on y is 1, and then this is a 3 as a constant. And the coefficient on x is now 3, and then -2 for y, and then 4 over here. And I'll draw a vertical bar to say that splits my constants from my coefficient matrix. So what's my goal, right? My goal is to get it so that it is in row echelon form or row reduced echelon form, where I have a diagonal of ones, and beneath that diagonal are zeros. So there could be a number here and numbers here, but the idea is of getting that diagonal of ones and having zeros beneath them. And I'm going to use row operations to do that. So here we go. I'm going to rewrite the matrix. I know you might be saying, why, we just wrote it. But trust me, you're going to want to rewrite it. This is a lot of writing, by the way, guys. It's a lot. So what I want to consider is how do I get this this form here, right? How do I get this? Well, I've already got the 1 up there, right? I've already got the 1 up in the top left. So we're going to do a sort of algorithm, a sort of suggested procedure. Now, you can really do these in any way you want. Okay, you can do them in any way you like. But it's really good idea to go column by column. So since this is a 2x2, it's easier, it's harder to see. But notice in my row echelon form, I have this first column, and then I have this second column, and then I have my last column here, right? Start with getting the 1 in the top left corner, then make everything beneath that 0. Okay? Once you have accomplished that, move to the next column, so this column. You don't care about this top one, you just care about the one that's in the diagonal. Get that 1 in the diagonal, then make everything below it 0. And then same for the last one. But you don't have to make anything 0. So, let's watch. Here's what I'm going to do. And I'm still going to use the idea of elimination and additive inverses here. I need to make this 3 a 0, right? So 3 plus what equals 0? Well, I need to subtract 3, right? I need to get rid of 3 somehow. But you can't just subtract 3. That is not how this works. Because what this matrix represents is a system of equations attached to variables. That 3 isn't actually a 3, it's a 3x. So you're not subtracting 3 from 3x, you're subtracting 3x from 3x. So, here's what I want to do. And this is how I'm going to model how you write row operations. If I take the first row and multiply it by -3, I'm going to take row 1. Notice I use R1 for row 1. I'm going to multiply it by -3 and take that result and add it to row 3. Figure out what that result is, and then replace row 3 with that. Or in other words, figure out this and put it into row 3. Replace row 3 with this. Okay? So watch. Just watch what happens. -3 times row 1. I'm going to take that first row and multiply by -3. This 1 times -3 is -3. This 1 times -3 is -3. And this 3 times -3 is -9. So the top row is -3, -3, -9. The bottom row is row 3, which is 3, -2, and 4. I am going to add this. So 3 and 3 cancel to become 0. -3 plus -2 is -5. And -9 plus 4 is -5. So this result, this is what replaces row 3. So on the next line, directly below, please write this vertically. Please write this vertically. Start on the leftmost hand side of the page, go down vertically, and make this work very clear. Because you're going to mess yourself up. You're going to be lost if you don't keep it organized. So keep row 1 the same. It's 1, 1, 3. But the bottom row is now 0, -5. Oops. -5, -5. I don't like that -5. There we go. I'm going to detach my iPad from the keyboard. Undo. Okay. And that'll be a little bit easier to write. Okay, now let's proceed. So I've got my 0, right? Compare where we are. We are here. Compare this to our goal. We've got the 1, check. We've got the 0, check. But now we need this 1, right? That's what we need. We need that 1. So how can I make this -5 a 1? Well, I don't want to add 1 to it because if I do that, this 0 is going to be messed up by this 1. So I'm going to take, if I multiply row 3 by -1/5, so I do -1/5 times row 3, and I put that into row 3. -1/5 times row 3 is 0, positive 1, positive 1, and positive 1. So on the next one, I will keep the top row the same, 1, 1, 3, but on the bottom row, it's now 0, 1, 1. Like so. Now, we have put this into sort of Gauss-Jordan form. We've put it in row echelon form, which means we can now convert this matrix. I'm going to say goal achieved. We are now going to convert this matrix back into a system of equations. So let's do this. Convert back into a system of equations. I think I'm going to use a different color. I'm tired of red. Is that okay? Do you mind if I switch to green? Convert this to a system of equations. Now, keep in mind what your columns represented. X, Y, and constant. So, doing the first row, you have X plus Y equals 3. Doing the bottom row, you have Y equals 1, because you don't have an X. So if Y equals 1, then X plus Y equals 3 means X plus 1 equals 3 means X equals 2. So my final answer is X is 2, Y is 1. All right? And there you go. And I think, since we're dealing with matrices, you could write it as XY equals 2, 1. So I'm actually, both of these are fine. And that I told you, I think today, or whenever it was I saw you, that there are going to be 3 ways to write your answers. And if you want to use matrices to write this solution set, that's fine by me. And there you go. X is 2 and Y is 1. Okay, now that was an easy example. I'm just going to let you know that was an easy example. That was a 2x2 system. All I did were like 2 row operations and we're done. But notice I'm going slow, as this is really new. This is probably nothing like you've ever seen before. So let's do another. And this one will be a little bit more complicated, but that's okay. That's all right. Okay, next one. Example 2, solve the 3x3 system using Gaussian elimination. So let's convert this system into a matrix. So an augmented matrix. X is 1, -2, 1, 0. 2, 1, negative 3, 5, 4, negative 7, 1, and negative 1. Do a bar like that. Now remind ourselves, what's the goal? I would write this at the top of your paper. What is your goal? What do you want to make this matrix look like? Well, I would like a diagonal of 1s with 0s beneath, and then whatever numbers above to get it in row echelon form. And then I don't care, it does not matter what the constants are because that's what you're solving for. So that's my goal. So let's take a look here. I'm going to rewrite the matrix again. Here we go. 1, 2, 4, negative 2, 1, negative 7. I'm getting sleepy. 1, negative 3, 1. I feel like I'm going to pass out. 0, 5, and negative 1. All right. So, as I said before, the goal is to first get this column, make sure you get the 1, and then make the zeros beneath it. And then you'll move to the next column, and then you move to the next column, and so forth. So let's just do this one at a time. I want to throw too much at you. If you get really good at this, you can start doing multiple row operations in the same matrix, but I want to take it slow, okay? Take a look at row 2. Having this 1 here, this guy, that 1 can easily eliminate 2 and can easily eliminate 4. So what I'm going to do is take, if I multiply 1 by negative 2, that is the additive inverse of 2. So take row 1, multiply it by negative 2, add that result with row 2, and put that into row 2. Replace row 2 with that result. So let's do that. Negative 2 times row 1, you're going to be looking here. Multiply that top row by negative 2. You get negative 2, positive 4, negative 2, 0. And then row 2 is beneath. And we're just going to copy that. And add. And now those cancel, and I'm left with 0, 5, negative 5, 5. So beneath this, and I will admit, this is the tedious part of matrix manipulation. You need to keep the top row the same, and the middle row is changed because I replaced row 2, and the bottom row is the same. So all I did was replace row 2. Okay. Now I've got that 0 down there. Can I make this 4 a 0? Well, yeah. If I take negative 4 times row 1 and add that with row 2, oops, not row 2, but this time row 3, and replace row 3 with this, then let's do that. Negative 4 times row 1. So look at your row 1. I'm going to use my laser pointer. This guy, the top row. Multiply negative 4 times all of those numbers. Negative 4, positive 8, negative 4, 0. And then row 3 is 4, negative 7, 1, and negative 1. And I'm going to add this. The 4's cancel. Which was 0, 1, negative 3, negative 1. And beneath, I will write that next matrix. Notice I keep the top row the same. 0, 5, negative 5, 5. And the bottom row is what changed. 0, 1, negative 3, negative 1. Like so. Okay. Okay, we're doing good. We're getting there. We are. Now, I want you to take notice. By the way, the rules I'm using, all of these row manipulations, come from this. Remember, and this is kind of the hard part of remembering, you can do either of these three things. You can change rows, you can swap them, you can multiply rows by non-zero constants, which is what we've been doing, and you can add multiples of rows to another row, which is that's the main thing we're doing. Now, I noticed one of the rules was swap. Notice this 1 here, I could put this here by swapping the rows. And this would be okay because these zeros are not going to change. So I'm going to take row 2 and swap it with row 3. So now I'm going to keep negative 1, negative 2, 1, negative 2, 1, 0. And now the middle row is now on the bottom. And the bottom row is now in the middle. And I do that. Okay, we're getting there. We're really close. We're actually very close, which is really, really quite great. So I've swapped my rows. And now, how do I make this 5 a 0? Well, if I use the previous line, use that 1 here, if you multiply that 1 by negative 5, it'll get rid of that 5. So I'm going to take negative 5 times row 2, add it with row 3, and replace row 3. So when I do this, I get negative 5 row 2. Multiply row 2 by negative 5, you should get 0, negative 5. Is that 15? And positive 5. And then row 3 is 0, 5, negative 5, 5. Add these. I'm going to get 0, 0, 10, 10. Is that right? Okay. Ooh. Now what? I guess I got to go to the next page, huh? So, here's what I'll do. I'm going to lasso this. I'm going to copy. Can I copy? I'm going to go to the next page. Okay. From previous page. I just kept that there so you could visualize it as we keep going. So now, I make my matrix. And guys, please don't be afraid to use paper. Use as much paper as you need. 1, negative 2, 1, 0. 0, 1, negative 3, negative 1. And the bottom row is now 0, 0, 10, 10. We are almost there. I've got my 1 here, my 0, my 0, my 1, my 1. The last thing is to make this 10 a 1. And if I divide by 10, or really if I multiply by 1/10, that will accomplish that. So take 1/10 times row 3 and replace row 3 with that. You're going to get this top. Sorry, copying all that down. But the bottom is going to be 1, 1. Hooray! this is row echelon form. Okay? This is row echelon form. Of course, we're not done, but from here, you can use this matrix to solve for the remaining variables. So I'm going to switch back to that green again. This is x, this is y, this is z, this is your constant. So rewrite the system of equations. 1x minus 2y plus z equals 0. 1y minus 3z equals negative 1. And z equals 1. Because there's no x, there's no y. Minus 3z equals negative 1. Okay. And from here, you just use this to solve, right? Y minus 3z equals negative 1, but z is 1. So y minus 3 equals negative 1. Add 3 to both sides. Y equals 2. And now use this information. X minus 2y plus z equals 0. But y is 2, so x minus 2 times 2 is 4. Z is 1. So x minus 4, okay, that's x minus 3 equals 0. Therefore, x equals 3. Right? I don't want to circle those. X equals 3. Okay. So, my final solution, I'm going to say final answer. You can write this as an order triplet or as a matrix. Since we're dealing with matrices, I'm just going to use that, a vector column. I sure hope that's what it's called. If you are a college professor or a college student and you would like to correct me on my verbiage, please do so. I don't know if maybe you've stumbled upon this video somehow for my Algebra 1. Wow, is the answer really 3, 2, 1? That's kind of funny, huh? Well, there you go. Answer was 3, 2, 1. Oh, bless whoever made this problem, because I did not make this one up. I found this one online, because making these is really hard. Construct like solving them is one thing, but creating them is another. Oh, but that looks so beautiful. Oh, that's gorgeous. Oh my God. Oh, just look at that. I mean, can you just take a minute to admire this? Can you look at that? Can you look how beautiful that is? I mean, I just think that's wonderful. So there you go. That is what Gaussian elimination looks like. See, it's kind of easy with the 2x2, but when you do it with a 3x3, you got to do multiple steps. It's kind of like solving a puzzle, right? It's kind of like solving a puzzle. Okay. I think I've talked for long enough. This is a super long video. I don't even know how long. I don't even know what the runtime is. It's probably an hour or more. I don't even know. It's almost midnight, and that's sleepy. I want to go to bed. So I'm going to do that. I will, however, post another video later, maybe over the weekend or something, going over that identity matrix idea. So what we're actually doing right now is called Gauss-Jordan, because we're kind of shortchanging the real Gauss with this goal of putting the upper triangular form. If we did upper triangular and lower, that would be true Gaussian. And what I mean by that is row reduced echelon form. And that's where you have the zeros up here too. You use the same, you can keep going, and I'm just going to do a video showing that. But you can keep going. You don't actually have to convert to the system. And if you're taking linear algebra in college, I'm sure that's what your professor's making you do. So, okay, there you go. I hope this was helpful. I know it was a lot, but embrace the challenge. We are in advanced algebra 2. Just take it headstrong. You're going to be great. You're going to do great. All right, take care.